Right, next I'd like to talk about the seasons and how they affect the climate of the Earth. So we can think of seasons as being caused by the tilt of the Earth's rotational axis. And so that would make a lot of sense if we knew what the rotational axis was. Let's define that first. We can think of the rotational axis as being an imaginary line that we draw through the north and the south pole of the Earth, such that if we spin the Earth about that axis, we get the rotation of the Earth, which is a counterclockwise rotation as viewed looking down on the Earth's north pole. And so this tilt then is with respect to the vertical, and the vertical is measured with respect to the ecliptic plane. And so here's the sun, and then the Earth goes around the sun in a plane that also contains the other planets called the ecliptic plane. So this angle is an angle of tilt from the vertical to the ecliptic plane, and is about 23.5 degrees. Okay, and so where did this tilt come from? Well, we think that it may have come from the collision that formed our moon, which we discussed earlier. And we know that today the moon helps to stabilize the Earth's rotational axis, so that without the moon, the Earth's rotational axis would tend to precess chaotically. And so the moon then holds the Earth's axis in place with a small range in angular shift between about 21 and 25 degrees over a 40,000 year time period. But basically, just put simply, the moon, because of its gravitational tidal effects, is able to hold the Earth's axis in place and create climate stability. And so we have these seasons, and these seasons are very beneficial for life, as we'll discuss a little later. But the essential idea that I wanted to emphasize here is that this tilt preferentially gives either the northern or the southern hemisphere of the Earth more light. And so when the Earth is tilted toward the sun, like this, we have the first day of summer. In the northern hemisphere. We define the northern hemisphere as being everything to the north of the equator. Okay, and so we can see then that with the Earth's axis leaning toward the sun, the part of the Earth that's getting light is this half. There's the sun, so it's going to illuminate the side of the Earth that's pointed toward the sun. And so this means we're going all the way from the equator to the North Pole and then some. The northern hemisphere is getting more than its fair share of the light. So associated with this then, we have the sun appearing higher in the sky. The days are longer. The night's shorter. Okay, and the reason the sun appears higher in the sky is that here you are, say standing in this location, you look straight up, it's a relatively small angle to adjust from looking straight up to looking at the sun. So alpha is a small angle. Meaning that you're looking from straight up through a small angle to see the sun. And so that means that the sun looks like it's very high in the sky. Whereas if you're down here at that same latitude in the southern hemisphere, you look straight up, then you look at the sun, it's a big angle, so theta is large in the southern hemisphere. So that means the sun is low in the sky. And so therefore, this is the first day of winter in the southern hemisphere. Okay, so the northern hemisphere has seasons that are different from the southern hemisphere by 2 seasons, essentially. We can see here that the northern hemisphere is getting more than its fair share of the light all the way past the North Pole with the sun higher in the sky. But here we're just getting this little slice of the southern hemisphere. And so at this time of the year, Antarctica would never even see the sun. Okay, and so this creates quite a bit of a difference in the climate that is associated with the summer months in the northern hemisphere, and then it can be quite a shock if you go to the southern hemisphere. This happens around June 21st, depending on whether it's leap year or not. This date can change slightly, but that is when the days are the longest and the nights are the shortest in the northern hemisphere. But the reverse happens in the southern hemisphere, where the days are the shortest and the nights are the longest. And so on the first day of summer, a few years ago, I flew to Australia, to Sydney, Australia. And I was in for quite a shock, not only because of the jet lag, but because the temperatures had dropped significantly, even though I was at a similar latitude to where I was in the northern hemisphere. And the length of the day was very short instead of being very long. And so they don't tell you about that adjustment. They just say, well, watch out for the jet lag. But there's also this adjustment to the seasons when you switch hemispheres at an extreme time like this. And so a lot of times in the southern hemisphere, people want to travel to the northern hemisphere if things are too cold for them in that part of the world at that time. And vice versa. When it's winter for us, a lot of times we'll want to go to the southern hemisphere for a vacation. And so this would happen 6 months later. Here we imagine the Earth's rotational axis has some kind of gyroscopic stability. And so by the time that it gets over to here, now the Earth's axis, although it's pointing in the same direction, relative to the sun, the Earth's axis is leaning away from the sun. Here I'm drawing the Earth much bigger than it actually is relative to the sun. So we can see that this is still a 23.5 degree angle from the vertical. But now we see that it's the northern hemisphere that's getting less light. We're only getting light up to here. This is all that the northern hemisphere is getting in terms of the light. Then the southern hemisphere is getting quite a bit more light, all the way down to the South Pole, and then some to the other side of it. And so this is the exact reverse situation, where if you're at a certain latitude here, you look straight up, then you look at the sun, you're looking through a relatively small angle, alpha, but in the northern hemisphere at that same latitude, you look straight up, that's this way, you look at the sun that way through a much larger angle, theta. And so this is the first day of winter in the northern hemisphere. That's 6 months later. So this is around December 22nd that this happens. But because of the fact that the southern hemisphere is getting more than its fair share of the light, this is the first day of summer in the southern hemisphere. So the seasonal effects are not due to the fact that the Earth gets closer to and farther away from the sun. Because as it turns out, the Earth is actually closer to the sun on December 22nd than it is on June 21st. So what that tells us then is that being closer to the sun is not as significant in this case as the amount of light that you're getting that is associated with the tilt of the Earth's rotational axis. So it all has to do with the tilt and not with the distance of the Earth away from the sun. Now, in between these two seasonal variations, we have spring and fall. And so, because the Earth is going around the sun in a counterclockwise direction, as viewed looking down on the Earth's north pole, just the same way as the Earth turns on its axis counterclockwise, it also goes around the sun counterclockwise. So it would come out of the board like this in this picture. By the time that it gets to here, around September 22nd or so, we have the first day of fall in the northern hemisphere, the first day of spring in the southern hemisphere. So this is what we call the equinox. When the Earth's axis leans toward the sun, we have summer for us. When it leans away from the sun, we have winter. But in between, we have this kind of a situation where the sun, imagine its rays are coming straight down now on the Earth. So we have equal illumination of both hemispheres. So this is the northern hemisphere, this is the southern hemisphere. But the rays are coming into the board or out of the board. Okay? And so we have equal illumination. Of both hemispheres. When the Earth's axis is sideways. It doesn't lean toward or away from the sun. So these are called the equinoxes when this happens. It happens 2 times a year. And so equinox just means the day length equals the night length. So this happens on September 21st. So that's the first day of fall in the northern hemisphere. And the first day of spring in the southern hemisphere. Okay, so that happens when the Earth on its axis gets to this point. So this is June 21st. And then we get to here. This is around September 21st or so. Then it comes around to that point. and then it goes behind the board, and then it's leaning this way, but it's behind the sun on that side. And so that happens around March 22nd. Which is the first day of spring in the northern hemisphere, and the first day of fall in the southern hemisphere. So if we want to take a look at the data projector for a second, we can see a couple of these things summarized. The rotational axis, a line that extends through the north and south poles of the Earth. The normal direction is vertical, which intercepts the ecliptic plane at right angles, and the rotational axis is 23.5. And so here then is a picture showing a little bit of perspective on all of these different variations that I discussed. When the Earth's axis is leaning toward the sun, summer in the northern hemisphere, winter in the southern hemisphere. When it's sideways, in other words, it's not leaning toward or away from the sun, it must do that because here it's leaning toward the sun, here, 6 months later, it's leaning away from the sun. So there must be a point where it's sideways with respect to the sun. And we get equal illumination. So that's autumn or fall in the northern hemisphere, spring in the southern hemisphere. Then we come around to this point on the other side. Following winter in the northern hemisphere, we have spring, equal illumination of both hemispheres. We have spring in the northern hemisphere and fall or autumn in the southern hemisphere. Okay, so that concludes our brief discussion of the seasons.